Okay, in this first section, we want to continue to talk about applications of definite integral, following what we've talked about at the end of Calculus 1. Okay, first of all, I want to show you how we first came up with the definite integral. Okay, in Calculus 1 or Math 140 at Penn State, we learned given a function with the graph showing like this, say we want to calculate the area of the shaded region. So what we do is to slice the region into n parts. Each part we create a rectangle. So the width of the rectangle is denoted as a delta x. The height is the function value at, for example, the right end. So the area of this strip is approximately the height times width. Now, since there are n strips like this, so the total area is approximately the sum of these n products. Mathematically, we can show if n goes to infinity, the limit of this sum is going to be the exact area. Now, this sum is what we call the Riemann sum. It's one type of Riemann sum because to create the rectangle, we could pick up the right end to evaluate the function as the height, or we could pick up any point within the short interval to find the value as the height of the rectangle. So just you know, the Riemann sum can be generally x sub I, say delta. No, I'm sorry, not delta. X sub I star, which represents any point from the short section. So we can do that. In calculus, for practical reason, we usually pick up the x sub I as the right end point, because there's formula we can develop for those right end points. We could pick up this point as mi, that be like a middle point. Each short section we pick up the middle point. Okay, so so in general, any sum like this is called a Riemann sum. Now let's back to the limit expression. So the limit of this Riemann sum is going to be the exact area. Well, from Math 140, that's Calculus 1 at Penn State, we learned it's very complicated to evaluate this expression because first of all, there's not a work involved just to even set this up. Now, setting up the Riemann sum is one thing. Being able to evaluate or simplify the sum is a big problem. Even if it can be simplified, it's complicated. We do limit. So anyway, general, if possible at all, such limited expression is very difficult, very complicated to evaluate. And well, just for the notation itself, for simplicity, we denote this limit as an integral notation, using this integral notation. The expression on the left side kind of summarize what's going on, on the right side, the process, the computations involved. So the same region, same problem. Let's look at a different way. Okay, well, it's the same idea, but we're going to just kind of skip the details and emphasize on the ideas involved. So again, we want to consider the area of this region. This time we say let's slice. Of course, we always slice. Okay, and then pick up a strip so narrow, so the interval is so short, so the strip is so narrow. Now, since we're going to take n strips through the process, you remember n will go to infinity, so this strip is very, very, very narrow. So instead of saying, oh, we're going to pick up the right endpoint or midpoint, evaluate function as a height, we just say, just some point x. So naturally, the height will be f of x. The width, of course, is still delta x. Then we do f of x. Now delta x, instead of using delta x, is dx. It's the same thing. Delta x represents the action increment, so does dx. Just different notation. So the height times width, that would approximately represent area of one strip. Now we add them up. So we use stretched s to represent summation, just same as summation there. Okay. Now we say, we're going to add from end A to end B, from the left end to the right end, like before. So it's like here. So naturally, we end up with this notation. So it kind of makes sense. Anyway, this is how we come up with this very important definite integral notation. It also presents to us a formula that we use to evaluate such complicated limit expression, because as you recalled in calculus 1, there's a different way, much simpler way to evaluate definite integral. So our job in this section is to work on some problems like this by finding the value of its equivalent definite integral. Also, we'll see a few other examples where we set up mathematical model which turned out to be definite integral. So this is what this section is about. Alright, let's first see some examples how we find the value of a limited expression like this by evaluating an equivalent definite integral. Alright, first let's find the limit of this Riemann sum. So here we use x sub I star, meaning just some arbitrary point from those short intervals. Okay, so let's look at the formula we're going to use one more time. So to go from limit of Riemann sum to definite integral, notice the limit summation becomes integral. Sine delta x is same as dx. The function turn to the function. So whether you have x sub I or x sub I star or mi, all turn to just x. Okay. Now with this, let's see how we first transform this limit expression to integral. So limit summation becomes integral sine -1, 2, 3. That's a and b. Delta x becomes dx, and the expression is the function we're going to have to integrate, called integrand. So we're going to have 3x squared minus 1. So this is the first part according to, well, the formula. Alright, next we evaluate this rather simple integral. So going to find antiderivative first. Copy down the 3. Integral of x squared is 1 over 2 plus 1. X to 2 plus 1. Integral of 1 is 1 times x. I applied the integral of power formula, integral of a constant formula here. And there's a 3, there's a -1. Okay, so let's simplify. 3 cross out. This x to the third power minus x 3 -1. Plug in 3 to the third power minus 3. Remember, plug in the upper limit for x first. Okay, upper limit for x, lower limit -1 for x. And just simplify. That's 27 minus 3, and this is -1 positive 1, so it's 0, so it's -4. So we find the value of this limit expression by first of all turning this to a definite integral, and then evaluating the integral 24. Okay, I'm going to show you another example. Again, we start with the limit of a Riemann sum. Notice this time we got mi. That just means it's the middle point we use to set up the Riemann sum. Alright, so first, again, we're going to turn this into a definite integral. Limit summation becomes integration sine 0 to 4. That's a, that's b, 0 to 4. The delta x is dx. Well, the main structure is our function or integrand here. So middle point turn to x, middle point turn to x. Now we have a definite integral. To evaluate this definite integral, we'll try to apply the substitution technique, because there's no direct integration formula we can use to find the antiderivative. So we do substitution, and we do substitution in writing. It's very important. U equal to x squared plus 9. This way, the radical becomes square root of u. Now what about the dx? Well, as you recall, we need to find how du and the dx are related. So let's find the differentials on both sides. Differential of the left side is du, differential of the right side is derivative, which is 2x times dx. That's how we find the differential. Now, from this equation, we find that x times dx equals 1/2 u. And the x and the dx are exactly the leftover, because we already turned this into square u, so it's just perfect. X times dx, same as 1/2 du, so we replace x dx by 1/2 du. Now, I'm not worried about the change of the limits, okay, because I'm going to use the original limits. Once I find the antiderivative and bring back x. Okay. So this is basically the power. By the way, the half constant factor put in the front. then just apply power, integral of power formula. 1/1/2 plus 1 u raised to half plus 1. Now I'm not going to put the limits here because it's still u, right? So this is a 3/2, so it's 1/3, and the u now replaced by x squared plus 9, and this is 3/2. Since x is back, now I can get my original limits back. Okay, then plug in 2 for x. 2 for x, 0 for x, lower limit. Now simplify. This is square, right? So it's a 4 plus 9 is a 13. So 13 raised to 3/2 power minus 1/3 times 9 raised to 3/2. So with a calculator, then you find the value. Okay. So now we've seen 2 examples at how we evaluate. What's this? We evaluate limit of a Riemann sum, because the formula, the definite integral formula. Okay, in the remaining of section, we're going to see some additional examples and see how we can do definite integral to solve some practical problems. Okay, the first example we're going to see is mass, total mass. Alright, suppose we have long thin rod. By the way, let's place it on number 9. So the rod occupies interval a to b. Well, suppose we know the density distribution function, rho x, meaning at each location the density is mass per unit length. Alright, the question is, what's the total mass of this long thin rod? Well, since the density varies from point to point, it's impossible to directly calculate the mass. What we do is to slice this rod, pretty much like how we slice the region in area computation problem. Okay, so what we do is pick up one short section and take out, say enlarge it so see better, right? That's one section of the rod. Suppose the width is very small, called the dx. Okay, now let's try to find the mass of this thin piece first. If we find the mass of this thin piece called the delta m, then we add them up, because we slice the rod into many infinitely many actually sections, pieces. Okay, so now the question is, what would be the mass of this short piece? Well, since this is so short, this piece is so thin, we can take the density at any point across and roughly consider the density to be the same from one side to another because it's so thin. Alright, so this way the mass of this short piece would be the density times the length. Alright, now of course, to write down the detailed Riemann sum, we say summation 1 to n, then send n to infinity, the whole process, which we're not going to repeat here. Instead, we'll just say, alright, now I got the mass of one piece. The total mass would be the sum of all those pieces, a to b, rho x dx, would be the total mass. So this is how you can see we end up with again a definite integral. Alright, so the idea involved is the same. We slice the rod, we think of the density across each piece to be almost the same, like a constant. Therefore, we can evaluate the mass of each short piece and add them up. Alright, so this is how we calculate total mass of a long rod when the density is not a constant. So let's just see one simple example. It's very simple. Okay, suppose we have a density function giving us 60 minus 2x. Interval is 0 to 25. So what's the total mass? Well, total mass is just a simple integral, 0 to 25 mass function rho times x increment. This will be the total mass. Now, this is just a matter of evaluating a very simple definite integral. So find the antiderivative 60 times x minus 1 over 2x squared. There's a 2, we copy down first. So it's a 60, to simplify this a little bit, 2.5 happen to cancel out. Okay, answer, well, plug in the upper limit again, 60 times 25 minus 25 squared minus 60 times 0 is 0, 0 squared is 0, so the answer is, well, with a calculator, I know of the square of 25 is 625. But anyway, so with a calculator, you can easily find the answer. So this is another a situation where we try to establish a mathematical model. Turns out, well, we end up with a definite integral. So it's considered as another application of definite integral. Alright, another application of definite integral is when we are given the velocity function of a particle, a moving particle. Alright, now question is, we want to know the distance traveled when velocity is given. This is time axis. Okay, so from time A to time B, what's the distance traveled? Alright, well, since the velocity is not constant, again, we're not able to directly calculate distance traveled. What we do is to slice again the time interval into many short sections. In each section, say time interval is with length delta t. So let's enlarge this time interval. Okay, so call it delta t. Right now, many intervals again. Any intervals will send into infinity. So infinitely many short, very very short time intervals. Now, our idea is similar. Okay, we'll try to find the distance traveled within each short interval. Now, since this is so short, we can say the velocity during this short time interval is always vt, and t is just any moment t we pick up within this interval. It's so short, so it doesn't matter where we pick up t, the middle or the right end or wherever, right? So can be considered, again, since this is a short time interval, so can be considered as the same as a constant. Therefore, the distance would be approximately velocity times time. Alright, well, then the rest we're going to add them up, right? We're going to add from time A to time B, all of those short distances. So the distance would be altogether A to B vt dt. Here again we end up with a definite interval. Now in this situation, actually it's not as clear actually what we get here. Okay, in physics there are two types of distance we are interested in. One is we just directly add it up. If we directly add up, this distance is called the net distance. The reason is velocity function can be positive, can be negative. You may be wondering, how could the velocity be negative? Well, you can say, some guy is traveling forward, and then the middle of the trip, and he changed his mind. He say drove back for some time, then drove forward, right? So when we add all this up, the distance can be forward, can be backwards. So when you add them up, in the end what you get is the net distance. It's the actual displacement from moment A to moment B, because this is plus minus cancellation. Think of this going forward, then backward, then forward. So when you actually measure up, that will be the from place A to place B. That's the net distance. Now, what's the other distance in physics that we're interested in? Mileage. So mileage is not the same as net distance. Mileage would actually double the part that actually repeated, right? So going forward, that's this much. Backward, that's added up. Then forward, so everything is added up. So that would give us the total distance. So the total distance, how do we get the total distance? Well, we still do this. We still consider things within each short time interval, but what we do is this time to ensure that when we add up, we actually add up everything. There's no cancellation, no plus minus canceling out things, right? So we make velocity positive, take absolute value of velocity, then add up. This time what we get is called total distance, or think of this like mileage. So either case, we just end up with just some definite integral. Okay, this one is straightforward. Given velocity, given the starting time, terminal time, just set it up, evaluate. This is similar, just mathematically. It's a little bit more complicated, as I'll show you in one example. Alright, either case, it's just a matter of evaluating definite integral, and this one is very, very straightforward, very, very easy. And this, I'm going to show you an example. Basically, just say how we evaluate such integral, right? When there's absolute value signs involved, how do we do it? All right, there's no integration formula we use to find the antiderivative. So through the example, I'll basically show you how to take care of the absolute value signs. So let's see one more example. Okay, suppose we have a velocity function as a 40 minus 26. We're going to go from 0 to 10. Alright, so I'm going to write it down. So if you're interested in net distance, you just set up directly this definite integral, which I'm not going to do because it's too trivial. Instead, I'm going to show you how to figure out total distance with absolute value signs. How do we find the antiderivative? Okay, well, there's, like I said, no formula, because no integration formula, because of absolute signs. So in order to evaluate, we got to get rid of absolute value signs. Now let's recall the absolute value expression. Okay, absolute value of anything is the thing itself if we know it's positive. It's negative a if we know it's negative. So the question now here is, what do we know about the 40 minus 26? Is it a positive or negative? Well, it's hard to tell. We're going to instead try to figure out the sign of 40 minus 26 from 0 to 10 algebraically. What we do is to first find where it's 0. So set 40 minus 26 to 0 and solve. Oh yeah, I think I made a mistake. It's not 26, it's 24. So let's change the number so we don't run into fraction. Alright, the method is the same. I just hate to work with fractions. Anyway, so 40 minus 26, I cheated. Okay, 40 minus 26 equal to 0. 24 moved over, you solve it, you get a 6, right? Nice. How about that? So we find out 40 minus 26 is going to be 0 at the 6. Now use this like 0 to divide the interval into two sections. Then we check the sign of 40 minus 26 over these two subintervals. Pick up a test point 0 to 6. Pick up any point 1, 4, 3, 1.9, whatever. Okay, of course we're not crazy. Let's pick up a 1. Pick up a 1 as a test point. 1 plug in for t. 4 times 1 minus 24 is negative 20. So I know it's a negative on this subinterval. 40 minus 24 is negative. Between 6 and 10, Again, we pick up any test point, like 9. You can pick up 7. Okay, any number is fine. So pick up a 9. 9 plug in. 36 minus 24 is positive. So I see it's positive here. All right. So now I know that the sign of a 40 minus 24 from 0 to 10. It's a negative from 0 to 6. It's a positive from 6 to 10. Therefore, I need to first of all break. This is how we deal with this kind of integral involving absolute value expressions. We break it according to the sign distribution 0 to 6. Six to 10. All right, this just to get ready. Now, here's the action. Okay, from 0 to 6, we know 40 minus 3 is negative. Algebraically, to throw out the absolute signs, we need to put a negative sign in front of the expression. Just that. Because 40 minus 3 is a negative, we need to throw a negative sign to make it positive. That's what the absolute sign is for. Okay. From 6 to 10, 40 minus 26 is positive. There's no need anyway, so we can throw out the absolute signs for free, just like that. So the rest is basically two simple integrals. All right, there's nothing complicated at all. Let's just find the antiderivative. 40, 4 times 1/2 t squared minus 24t. That's antiderivative. Integral power, integral constant. Upper limit, lower limit. Second integral, again, very simple. Find the power, first power, right? Antiderivative of first power is 1/2 t squared, and this is 24 times t. Then you plug in 10, plug in 6. So the rest is simple algebra. You plug in 6 for t, 0 for t, 10 for t, 6 for t. So this is a 2. So we have 2 times 6 squared minus 24 times 6. 0 plugging for t, minus negative becomes plus. Well, you're going to get 2 zeros anyway here. Second term, you plug in 10 for t. This is 2, by the way. You get 2 times 10 squared minus 24 times 10. That's when you plug in 10 for t, minus then 6 for t. 2 times 6 squared minus 24 times 6. Again, with the calculator, you would be able to find the answer easily. Okay, so I'm not going to finish that, but you need the calculator to do it. All right, so this is an example I want to show you concerning velocity, distance. Mainly, I wanted to show you how to find the antiderivative of an expression involving absolute values. The idea is you do some algebra first. You check out the sign of the expression. Create a sign chart. You set the expression to 0. Find the sign within each subinterval. Therefore, you can treat the absolute value signs appropriately. 0 to 6, that's negative, so you just put the negative sign in the front. 6 to 10, the expression is positive, so you can just throw out the absolute sign for free. Alright, so this is a distance problem. By the way, this is the total distance, what we call the mileage. You want to do that distance, well, it's extremely trivial because it's going to be just like one of those two anyway. Alright, so in summary, in the first section we learned how to evaluate some similar limit expression, limit of Riemann sum. How we did it was to turn this to definite integral. All right. Limit summation becomes integral sign. Function is the same function. Delta x increment, just dx x increment, right? Also, we discussed two situations where when we try to set up mathematical model, we end up with definite integral. So one was total mass, applying the same ideas. We come up with the definite integral expression. So we slice something. Originally, we were considering area computation, so we were slicing region. To calculate the total mass, we slice the long rod. To consider, traveling problems, distance, computation, we slice time interval. Okay, in each case, we focused on what happens within each short interval. Then find, what we want. Short interval, short time interval, find the distance traveled. Shorter section of rod, we find the mass of each piece. All right. So all of these are done based on the same concept. The Riemann sum, the limit of Riemann sum, which turned out to be definite integral. So in this sense, we've seen just two additional applications of definite integral. All right. The homework problems for this section are already posted online. You can find them on Canvas. Okay, work on the problems in this section, as many problems as you could. In particular, work on the odd number problems, because you can find the answers in the back. If you have any question, send me email, contact me. I can help you out through meetings.psu.edu online. Okay.